Hey, everybody. Hey. So I'm Kalman Lajko, I'm from ZK10, and I would like to talk to you about hyperscaling. Hyperscaling is the question of how an interconnected ecosystem of rollups should operate. This is basically the same question as execution sharding, just in the context of rollups. So the first topic we should cover is interoperability, and this is related to hyperbridges. Hyperbridges allow hyperchains to cheaply and trustlessly interoperate. The crucial part of this process is the message route, which is a commitment to all the hyperbridge transactions happening inside a layer 2 ecosystem between different layer 2 chains. And this is the only part of the messages that is sent to L1. And the core message, which actually contains all the information about the user's transaction, is sent directly from the sending chain to the destination chain, and it is there compared against this message route. So this allows hyperbridging to both be trustless and cheap. And using this process, it is possible to get an ecosystem of interconnected hyperchains. Hyperbridges allow general message passing, and also assets to be passed from one chain to another. So we get a unified liquidity across the whole ecosystem. And in order to ensure unified liquidity, layer 1 assets need to be logged inside a shared bridge on layer 1. So interoperability is the first part of the puzzle, but there are more questions, such as how to organize the chains, should you have layer 3s, fractal scaling, proof aggregation, and that's the harder part. Now let's look at those. So the first solution is proof aggregation. With proof aggregation, what happens is that multiple blocks of a simple hyperchain are first aggregated across time, and then these proofs of different chains are aggregated and settled on layer 1 together. Now, settlement on layer 1 is relatively expensive, so in order to minimize fees, it makes sense to settle less often. But this is bad for hyperbridging, because hyperbridging is only possible once settlement on layer 1 happens. So for fast messaging, this is not an ideal solution. So to fix this, we can have layer 3s. And layer 3s can settle on a layer 2, and because it's a layer 2, settlement is much cheaper there. And this is basically the same hyperbridging process as we saw before, but because it's happening on a layer 2, it can happen much more often, and so bridging is much faster. Now, if we look at more detail at what actually happens here, is that the blocks and the proofs of different hyperchains are first aggregated across multiple chains, and then the proofs of the layer 2 are aggregated across time. So in a sense, we are flipping the order of aggregation, first across chains and then across time. However, layer 3s still have some problem. There are two main problems. The first is scalability. The layer 2 has a virtual machine, which cannot handle an arbitrarily large throughput. And the second is that the layer 2 has a consensus mechanism which secures the layer 2 itself. And this layer 2 might revert, this consensus mechanism might revert, and this will cause the layer 3s to revert as well. So in order to solve this, we need to solve scalability and this middleman problem that the layer 2 causes. First, for scalability, we can just remove the layer 2's virtual machine. And if we remove the layer 2's virtual machine, we can have a specialized proof there instead. Then we can have a scalable and solution that is still good for fast messaging. And this specialized proof would still have a message route, so hyperbridge transactions could be verified from there, and this message route can be also imported back later there when the layer 3 settle on the specialized proof. But we still have this middleman problem because the specialized proof will still have a consensus mechanism. This is the aggregation layer in a sense. So let's look at the consensus mechanism that this specialized proof requires. It only needs a minimal consensus mechanism because it does not aggregate, process user transactions. It only processes hyperchain proofs. This means that finality can be much slower. It also does not have storage requirements, and it has minimal state because it only stores commitments to the hyperchain's states. This means that it has minimal data publishing and storage needs. In conclusion, this basically means that light clients are full nodes, similar to in data availability. Light clients can contribute to this consensus mechanism's security. Okay, so this hasn't solved the middleman problem yet, but let's look at how layer 1 solves this middleman problem. So currently, layer 1 is the most decentralized chain, and we have a small number of rollups settling onto it. So it is unthinkable that the layer 1 would have major reorgs. But in the future, if the whole ecosystem is processing 100,000 TPS, and we have 1,000 rollups, then the total stake in all of the layer 2s together might be bigger than the stake in the layer 1. To solve this, we can use restaking. All of the stake can be logged in the layer 1 consensus mechanism and restaked to be used in other consensus mechanisms. And validators can be run for the layer 1 and the layer 2 consensus mechanism in parallel. This makes the layer 1 very secure, as the stake securing the total ecosystem will be approximately equal to the stake securing layer 1. So this is how to solve the middleman problem, and we can use the same solution in the context of proof aggregation as well. We have the proof aggregation layer with the specialized proof, and we have the hyperchains. The hyperchains have the traditional consensus mechanisms, and the specialized proof only has the minimal consensus mechanism, which can be verified by light clients. The hyperchains are basically light clients of the proof aggregation layer, as they are using the message route from there to use for their own messaging purposes, and they also settle the message route inside the proof aggregation layer because it needs to be settled there. So we can actually measure the acceptance of the specialized proof's consensus mechanism by measuring the message routes that are settled inside the proof aggregator. So using this solution, it is possible to solve the middleman problem, and now we can have an ecosystem that has fast messaging, that is scalable because it uses proof aggregation, and it is also secure because the stake is distributed in a manner such that the proof aggregator stake is approximately equal to all the stake inside the ecosystem. So finally, I would like to cover one last topic, which is cross-hyperchain forced transactions. This will be very important in the future because if we have 100,000 TPS, then censorship resistance from the L1 will be very expensive because the layer 1 will only be able to process a certain number of transactions. So it's very important to have forced transactions going from one hyperchain to another. And this would be through a similar process as normal hyperbridges. Expect it wouldn't be a relayer that sends a transaction from one hyperchain to another. It would be sent to the data availability layer, and from here, the receiving hyperchain could import it. And to make sure that it is indeed imported and executed, the sent message route and the received message route would have to be compared inside the proof aggregation layer. Now, this is just an approximation because the actual construction is much more complicated because different hyperchains might settle at different moments, but this is the main idea. So using this construction, we can have fast messaging, we can also have scalability, security, and censorship resistance in the whole ecosystem. Thank you very much, and if there's time for questions.
We have a few minutes for questions. Round of applause first. Okay, these are lightning talks, so they're lightning questions also. So, any fast questions? Okay.
really high level, I mean, we have a few of these like stack kind of projects, like OP Stack or even Madara on Starknet. How does this, just fundamentally high level, how is this so different, or like, in terms of what we can do here versus other stuff?
So I would love to answer your question. The problem is that most of these stacks haven't really specified what their solutions will look like. So as you mentioned, Madara is just, as I understand, a sequencer for layer 3s. It's not the core part of the stack. Starkware never specified how their proof aggregation system will look like, neither did Polygon. I can address optimistic solutions, because for optimistic rollups, it's much harder to have interoperability. So every solution that uses ZK proofs will have much better interoperability than optimistic chains. I think for us, our biggest advantage is our great proof system, because I think our proof system and our VM implementation requires the least amount of GPU RAM to run. So this means that proofs can be generated in a decentralized manner, which makes the whole ecosystem much more decentralized compared to other solutions.
Okay, we have one more question.
This might be a stupid question. I know that this architecture is trying to solve like the fragmentation of liquidity, but are you also solving the fragmentation of like app deployments or infrastructure across these different environments? Like, does a Hyperchain 1, Hyperchain 2, like, do those all have to integrate with Fireblocks individually, or do frameworks appear so that you kind of have this like shared like framework where they can all interoperate?
Yeah, so all of the chains should have the same API calls, but if you want to deploy an account on a chain, you will have to deploy it on that chain specifically. And there will be ways of natively, so we will have methods of the concept of the same account of multiple chains. So I think that will definitely help a lot, but each chain will be its own chain, basically.
All right, thank you very much.